This video will explain the concept of an electric field. The electric field is defined as being a region or area where a charge will feel an electric force. An electric field surrounds a charged particle or charged object. For example, let's say that we had an electron. The electric field would be in the area anywhere around that electron. And I know that because if I put a charged particle, let's say for example I were to put a positive charge, sometimes we call that a test charge. If I were to put a positive charge somewhere near that electron, that positive charge would feel a force. Specifically, it would feel an attractive force because positives and negatives attract each other. Because that positive charge would feel a force there, that means there must be an electric field there. This concept is similar to what happens with gravity. We know that any time we are near Earth, we feel a gravitational force. We don't have to be in contact with Earth to feel that gravitational force. As a matter of fact, when we're up in an airplane, we feel that gravitational force. Or even as simple as jumping up in the air, we feel that gravitational force. That means that we are constantly in a gravitational field, as long as we are on Earth. The electric field can also be calculated, and it can be calculated in a couple of different ways. One method for calculating the electric field is by using the equation electric field, or E, is equal to the electric force that is felt by a charge divided by the charge of that object. In this equation, we will plug in a positive or negative with the Q according to if it's a positive or negative charge. You can also kind of figure out the units of the electric field based on this equation. We know the unit for force is a Newton, and the unit for charge is a Coulomb. And so the units for the electric field is newtons per Coulomb. And as you can see, it is also a vector, so it does have a direction. Another way to calculate the electric field is using the equation E equals KQ over R squared. This actually only gives us the magnitude, so I shouldn't have a vector symbol here. Now, this equation comes from a little bit of a derivation. I know that the force between two point particles has a magnitude of K, Q1, Q2 over R squared. And to find the electric field, I divide the force by Q. Well, this Q that I'm using is either 1 or 2, and it doesn't really matter which. So you'll notice that I'm left with KQ over R squared, which is what I have here. Now this equation can only be used when the source of our electric field is a point charge. That'll be the case in most of the problems that we experience. Now I mentioned to you electric field is a vector. In this equation, KQ over R squared only gives us the direction. Only gives us the magnitude. To determine the direction, we have to use something called a test charge. A test charge is considered to be a very small positive charge that does not affect the field itself. Basically, if we have some sort of field present, let's say that there's a field present in this kind of blank space, then if I were to take this test charge and put it in that field, it would feel a force. Let's say again, for example, that it feels an upward force. If that's the case, then I know that the direction of the field is up. The direction of the electric field is the same as the direction of the electric force felt by a positive test charge. Well, what happens if, for some reason, we have a negative test charge instead of a positive test charge? We can still use it, But we have to remember that the force felt by a negative charge is in the opposite direction of the force felt by a positive charge. Therefore, the electric field, the direction of the electric field, is opposite the direction of the force felt by a negative test charge. Let's see how all this comes together with a problem. In this problem, we have a small object with a mass of 3.8 grams and a charge of negative 18 microcoulombs, and it says that it floats in a uniform electric field. We're asked to find the magnitude and direction of that field. You'll notice the word floats is in quotes there. That's the key to understanding this problem. If I think about something floating, a lot of times I think about something that's in water. Well, when you float in water, it means that you're not sinking, right? Basically, it means that you're not moving up or down. In other words, this small object is in equilibrium. So, I know that if it's in equilibrium, the net force on this object is equal to 0. This object happens to have two forces acting on it. We know that there's the force of gravity. It has mass, therefore it has the force of gravity acting on it. And it's in an electric field. Therefore, we know that there's also the electric force. Adding those two together gives us 0, which means it's in equilibrium. Now, I've started by talking about forces, but the problem is really focusing on electric fields. But I know that there's a relationship between the electric force and the electric field. Namely, that the electric field is equal to the electric force divided by Q. Well, looking at my force equation over here, electric force is equal to the negative gravitational force. So that means that electric field is equal to the negative gravitational force divided by Q. Well, I also know that gravitational force is mass times gravitational acceleration. I'm given mass. I know gravitational acceleration, that's a constant, and I'm given charge. So I now have everything that I need to be able to calculate the electric field. The problem gives me mass in grams, but we know that when we're calculating a force, mass must be in kilograms. Therefore, I'm going to convert 3.8 grams into kilograms, which gives me 0.0038 kilograms. And there's a vector symbol on top of my g, so I'll use the negative 9.8 meters per second squared. In the denominator, I plug in charge, and I am allowed to use a negative sign with there. You'll notice there was no absolute value signs around that Q. So negative 18 microcoulombs. Well, micro is 10 to the negative 6th. So negative 18 times 10 to the negative 6th coulombs is what I have here. Plugging all that into my calculator, I end up getting negative 2,069 newtons per coulomb. But as we know, we don't leave negative signs to indicate direction. Instead, we use a word or an arrow. So the magnitude is 2,069 newtons per coulomb. And in this case, the negative sign indicates down. Another way to think about the direction of that field is thinking about the charge itself. My small object has a negative charge, and it tells me that it's floating. Well, I know gravity is acting downward on this object, and I know that if it's in equilibrium, the electric force must act upward. As I mentioned on the previous slide, the direction of the electric field is the same as the direction of the electric force if it's a positive particle, or opposite the direction of the electric force if it's a negative particle. Since this electric force is pointed upward, the electric field must be pointed downward then. Let's look at one more problem This one's a bit different than the last. The last problem wasn't a point particle. It gave us a somewhat significant mass. However, this problem is relating to point particles. We're asked to do two things. First, to determine the electric field strength at a point that is 1 centimeter to the left of the middle charge. I'm going to mark that point with an X. After we calculate that electric field, we'll then be placing a charge at that point and determining the force on that charge. That's where electric fields can become handy. If we know the field, then we know the force on a charge placed at that point. Starting off with part A, we need to calculate a few electric fields and then add them as vectors. So as I have done with forces, I'm going to label these charges A, B, and C. And I'm going to work to find the field caused by each of these charges. In general, I'm going to use the equation that the magnitude of the field is kq over r squared. And I'm going to plug in the individual q and the individual r in each case. So for example, looking at the field created by A, which I'll call EA, we have K, or 8.99 times 10 to the 9th, Newton meters squared per Coulomb squared, times the Q of A, which is 6 microcoulombs, or 6 times 10 to the negative 6th coulombs. We divide that by the distance from A to the point where I'm looking for the field, the point that's marked with an X. In this case, that distance is 2 centimeters, or 0.02 meters. And I can't forget to square that distance in the denominator. Plugging all that into my calculator yields an electric field from A of 1.35 times 10 to the 8th newtons per coulomb. Moving on to B. With B, the charge will change to 1.5 microcoulombs, and the distance will change to 1 centimeter instead of 2 centimeters. Again, don't forget to square your denominator, and don't forget to convert your units. It just so happens that I actually end up getting the same number when I plug those ones into my calculator as well. 1.35 times 10 to the 8th newtons per coulomb. Lastly, we'll find the field caused by C. Notice that I didn't plug in the negative sign with that direction. Similar to the electric field equation, similar to the electric force equation, the charge in this electric field equation is an absolute value. So I do not use negative signs when I'm plugging that charge in. This time I get 2 times 10 to the 7th newtons per coulomb. So the first step in doing this problem was to find the individual electric fields. But now I need to add those fields. Well, since they are vectors, I have to find the direction before I'm allowed to add them. So I'm going to take a look at my diagram to help find that direction. Remember how I said that the electric field direction was the direction of the force felt by a positive test charge? Well, I'm going to make up a positive test charge and put that positive test charge at my X, the point where I'm looking for the field. Then I'm going to look at each of those stationary charges, A, B, and C, one at a time. So this positive test charge, would it be attracted to or repelled from charge A? Hopefully you said that it would be repelled from it. A is positive and my test charge is positive. So they're repelled from each other. But I'm going to pretend like A is nailed down. It's not able to move. That means my test charge is the thing that can move, and it would move to the right. Because it would move to the right, the direction of this electric field is also to the right. Looking at the direction of electric field B, I'm going to pretend like charges A and C don't exist, and that B is nailed in place. Again, I place a positive test charge at the point in question, and I want to think about what happens to that positive test charge as a result of being in the electric field of B. Well, we know that the test charge is positive and B is positive, which means they repel. So if B is nailed down, the test charge would move to the left. That means that this electric field is also pointed to the left. Lastly, looking at the electric field from C, I pretend like A and B don't exist. They're imaginary, and that C is the only charge that's there. Putting my positive test charge at the X means that that positive test charge would be attracted to C, and so it would want to move to the right to get closer to C. And therefore, the electric field from C is pointed to the right. Since I have three electric fields that are all parallel to each other, when I'm trying to find the total field, which is equal to EA plus EB plus EC, I get to just add, putting in negative signs where something is to the left and positive signs where something is to the right. Looking at my numbers, I notice that the field from A and the field from B are the same in magnitude and opposite in direction. That means when I add those two together, I get 0. So the total electric field is simply the electric field from C, or 2 times 10 to the 7th newtons per coulomb to the right. This process is very similar to what we do for finding the force when there are multiple point charges. The only difference is that we don't have an extra Q in the numerator there. And it's a little bit different how we figure out the direction of that field. In class, we'll go over some more problems dealing with the electric field.